So I have a bombshell, which is that the whole Frametimes thing.
It's all garbage.
It's all wrong.
It's all garbage.
So Frametimes entered discussion along with 1% and 0.1% a little over a decade ago now. And that has been a driving factor of reviews. It's shown that average FPS is not enough.
Not enough.
It doesn't show the full picture. You can have super high average FPS, terrible game experience.
True.
But it's all wrong.
There's some things that can be improved.
Asterisk.
Asterisks,
Right.
Exactly. That's your hook.
That's the hook.
Nice.
We normally don't tell them that's the hook. This is Tom Petersen. That was the hook. Tom is an engineer at Intel. We've done videos in the past on measuring things like actually GPU busy right here.
Yeah, yep.
And this was a great topic. We did a canonical view of the pipeline.
Oh, that's right. We did. That's good.
And so general kind of technical engineering type topics about games and how they're perceived and problems with frame pacing and rendering and resource utilization is what we're talking about today too. But you have a PresentMon update that will give us a much better look at things.
I hope so, right? I hope so.
And I want to start too with PresentMon is an open source tool. So
it is completely open. You'll find it out on GitHub. It's been an Intel project for forever, and we've been improving it and making it better. And this is a big step for PresentMon.
And this is what, I don't know if I could say most or not, but a lot of the reviewers I know, including us, most people use PresentMon these days. It basically replaced Fraps. So, okay, so
let's dive in.
There's some cool stuff today. Animation's a big topic, I think.
I think it's going to change the way we think about things a little bit.
Do you want to start with why Frametimes are wrong? Before that, this video is brought to you by Arctic and the Liquid Freezer 3, which we've tested using our standard methodology and found to be one of the most noise-efficient CPU coolers on our charts. The Liquid Freezer 3 includes Ryzen offset mounting to improve AMD performance and uses a thicker radiator to further lower the temperatures. Arctic has priced these competitively for AIOs, and you can learn more at the link in the description below.
I think we should start with what have we been calculating so far.
Okay.
Okay, so what we have been calculating so far is Fraps' fault.
Okay.
Okay, because Fraps was a
throw them under the bus.
They're gone
anyway.
Right? Nobody cares. Yeah, so Fraps was a program obviously very important, but it was the first way we measured performance, right?
Yeah.
And it was a shim, which means that it hooked an API called Present. And so it kind of sat, if you thought about this, where's Fraps? Fraps measures from the time render ends, which is with a call called present, and then it stays and it measures until it sees another present. So Fraps is measuring what's called percent to present, which is a great approximation for frame time, right?
Yeah.
That's what we all saw. But now if you look at this chart, it's a little bit concerning because that time is across the blue weight.
It's not truly a frame.
It's not a frame. It's a frame interval, but it's measured across 2 frames. So what does it mean if this frame has a long thing and this had a short wait? Right. It's really not the same frame.
And this goes back to something I mentioned to you earlier, but years ago I did a discussion, I'm pretty sure we filmed it with Scott Wasson. At the time he was at AMD, he then went to Intel, and now he's somewhere else. But he
ML bench.
That's
right.
Yeah. But Scott was critical for early frame time discussion because he sort of debuted the whole written methodology of it from a media perspective.
Yes, great guy.
The reason I bring him up though is because at one point I noticed there was kind of a silent change in the charts where it went from frame time to something like frame to frame interval or something like that.
Yeah.
And so I think I finally understand why he made that change.
Yeah, I think that's why. I mean, I'd have to ask him why he made that change. That's how I have made that change.
Right.
And the reason I'm changing it is because suddenly it matters. And it matters when you start thinking about stutter and animation error. And the way to kind of get into it a little bit is if you know the frame time, then you can actually calculate basically the animation step for a frame. And the animation step is basically equal to the frame time mostly, right? There's some times where it's a little different, but what you need that for is to be correlated with the display time step. Because if the display time step is different from the animation time step, you'll get a simulation time error, which is measuring stutter directly for the first time. So the reason we're changing this is because, first of all, it's more consistent to measure frame time in the correct spots in the pipeline, but also it makes it possible for us to directly measure what we're going to call simulation time error.
Yeah. And so this is I think this is kind of the key component of frame times as they've been presented so far. inaccurate or all wrong. A little bit of a
Definitely not all wrong.
little bit of a stretch.
A big stretch. They're mostly right,
but there is more to it. So
yeah.
this I was genuinely really excited about seeing, 'cause just like GPU Busy when you brought that by. We've used GPU Busy a couple times. It needs like one more step to really truly make it into the review cycle.
I think so.
And it's getting there. But the reason I was excited about it is because you're always looking for how can GPU and CPU reviews be improved. Because if we are at endgame, that's very sad.
I don't think we're at endgame.
Yeah, and they're pretty good. But for reviewers, there's limited insights we have access to, whereas hardware vendors can see a whole lot more.
Well, you saw from the talk earlier, right?
Yeah.
There's a lot going on there.
And so stuff like this should hopefully start
I
opening
think
up
so.
more
I
of
think,
that.
I mean, we're making it open source. We're going to keep iterating on it. But the big changes this time are, first of all, we're lining up the frame time correctly. Now we're breaking out CPU busy and CPU wait and CPU start. By the way, all these names that you see are now going to appear in the spreadsheet that is captured. When you do a capture, you'll see all these names. So it's a little bit more clear what you're looking at. GPU time is now measuring the time from once the GPU starts rendering to the time it stops rendering. So that's pretty cool. And we actually break it up into GPU busy and GPU wait. So a lot of the times,
so that's new.
That's brand new.
Yeah.
A lot of times the GPU is doing multi-pass rendering, and it can actually be idle even though you started render and you're not done yet. So breaking it up now exposes, hey, wait a second, is my GPU really busy or is it stalled waiting on the CPU?
Let's recap some of this. We did talk about this in depth in a separate thing.
Yeah.
I think it's worth bringing it back though. The framing I had last time to try and help everyone quickly identify where's the use was identifying bottlenecks is kind of an obvious one.
Yep.
But can you walk me through again why the breakout here?
Is
what
useful?
Extra insight does that give?
Having the GPU wait would tell you, is there some kind of codependency on the CPU threads that are actually causing my GPU time to be extended.
Okay.
Right, and so you might think that you're having a very large render and that you would think that's 100% GPU utilization, but the truth is it's not. And having this GPU wait gives you that one more insight into there's some kind of funky interdependence between the CPU and GPU that's not allowing the GPU to be fully, utilizing itself.
So previously, if you saw just a long GPU busy here, without that weight in the middle.
Yeah.
Am I correct in understanding that makes it appear like it's all GPU bound, but actually some of it's weighted on the CPU?
Yeah, a lot of it's CPU. Because you'll see in certain games, the GPU busy as a percent of frame time can actually be quite small, right? And so that's a very important insight into how should I be balancing my CPU and GPU.
And let's bring that back up as another refresher. So when talking about GPU versus CPU utilization during the time a frame is being rendered, I don't really want to frame it as like what's the ideal, but what kind of split are you looking for the balance between the two parts?
I would love for the GPU to be fully fully utilized, but the problem there is that you don't know you're running your worst case scene, so maybe you want your GPU to be slightly not fully utilized. But if it's not fully utilized, that's the big thing that you're trying to do, and you'd like to adjust your CPU so that it's
also probably the highest cost.
It's also the highest cost, right? So you're looking to kind of utilize that highest value thing in your system. So I want to push the CPU as much as I can to feed that GPU. And if I see I've got the settings messed up, where I'm just putting too much load on the GPU, I will know it by looking at my sort of GPU busy relative to frame time or relative to CPU busy.
How about simulation time error on the side over here?
Yeah, that's cool. So that is the thing that we'll be introducing probably by the time we put this beta out in public.
Is that the missing link?
That is the missing link. Yes.
We found it.
Okay, so simulation time error is talking about something that if you've been listening, you know what I'm talking about. So if people have not been listening to me, it's this stutter thing, right? And we all know that when you're playing a game, if it stutters or it hitches, it's not a great experience. But there's also a thing that's happening all the time, which I call micro stutter, which are these like barely perceptible little jitters to things. And those aren't great either. So this is the first time we're going to measure those directly. And what Scott did was said 99th percentile, 95th percentile, 90th percentile. Those are kind of proxies for stuttery things. And they are in one sense, but they're not actually directly measuring.
So I can add to that too, where similar but a different calculation for us. We talk about this in reviews though. When our approach is bar chart for broad picture, and then if we use 1% low and 0.1% low, a little different calculation than what Scott did. If we see one of those drastically out of step or just really bad,
Yeah.
that tells us now go draw a line graph
Yeah.
for frame time.
Yep.
But you're saying, so what I've been saying, and this is the the asterisk a little bit wrong part for everyone, but what I've been saying is if the 1%, 0.1% is low, that is the proxy to get us to the frame time line plot to tell us this is the problem. What you're saying, the frame time line plot is still kind of the proxy to get us to the...
to this.
Okay.
Right? Because what you actually care about, there's a lot of perceptual things here. A big, fuzzy frame time chart is not good in and of itself.
Right.
Even if everything is paced perfectly, you're still going to have this long, short frame, and your brain kind of sees that as a blur. So you want frame times to be fairly uniform just to avoid that phenomenon.
Is there another step after this? Are you going to come back in 5 years and be like, I found it?
There's one more. Just one more.
Right.
No, but in this case, simulation time error is going after that thing directly. And the thing is stutter. And that's exactly what simulation time measures. It doesn't measure like a variation, which is what the frame time stuff is measuring. This is measuring directly the error.
So what is happening during simulation time? What is that?
So simulation time is every frame when it's generated on the CPU has a time that it's sort of modeling, right? And so if you did 10 frames in a row, they'd all have 10 numbers of what time do they represent sequentially. What you want is that step between those times to be fairly uniform. That'll give you fairly, good uniform experience, but you also want them to show up on your monitor with the same relative spacing. Because if they move around on the monitor timing, that will manifest itself in simulation time error.
And I think this, using simple words, but genuinely one of the better pictures of it is when the game just sort of feels bad, but you can't quite explain it. That's it. Kind of that stutter.
I mean, there's lots of things about, like, if the frame rate gets too low, it just sort of sucks. If the frame rate is inconsistent, it just kind of sucks. And this is very directly measuring that second and
so why has it taken this long to get the simulation time error then? Because we're talking the frame time discussion, you were, as I understand it, heavily involved in.
I had a little something to do that back in the day.
Yes. And at that time, that was also one of those, why did this take so long to discover? So, I mean, if you're able to look back at it, why are we getting to this now? Like what brought this up, right?
Why are we doing this now?
Yeah.
Well, it's because...
Why don't you just give me the best thing immediately?
We kind of, it's an iterative thing. And actually every idea I've ever had, Stephen, has always been that kind of like, well, that's obvious. That shouldn't even be a patent.
Sure.
Yeah, same idea, right? But this is not new. I mean, people have been aware of simulation time error for a long time, but we're uniquely positioned where we make PresentMon. And PresentMon is everywhere. And I've been managing to convince Jefferson, who's the godfather of PresentMon. You've spoken to him several times, Jefferson Montgomery. Great job. He's into it now, right? And he's trying to help us, and we're helping him get that next level.
How does simulation time error? So two-part question here. First one is you're talking about even spacing, which I guess from a user standpoint kind of manifests itself as like animation fluidity or something.
Smoothness,
Right. How does it look on a chart or a graph?
You mean how does animation error look?
Yeah. Is this something I can make a number? Okay.
You can. I mean, when you use this, you can, but you can't do it today because simulation time error requires two things. You need to know the animation time associated with every frame, and you need to know the time that frame is being flipped. And so, like, relative to each other, you need both of those data points. So today, people are mostly using CPU start as the animation time, which is a pretty good proxy, and that's what we're going to be doing initially. There are explicit APIs, both from NVIDIA and from us and others, that are allowing game engines or games to tell you that animation time. And so as that becomes more available, we'll be building that into PresentMon.
I see.
Yeah.
And to loop it back into the question, when it is all functioning as you kind of envision it to, is there a chart with the number I can make?
Yes, there is.
Okay.
Yeah, so the chart I would make.
That's what I need,
Eventually add up all the simulation time errors. That's a number in milliseconds. Okay, and that gives you, if I ran my test for 10 seconds, I had 80 milliseconds of simulation time error. That by itself is hard to get a sense of, so divide it by the total test time. So if you divide the simulation time by the total test time, that'll tell you basically a error per second metric.
Some kind of rate.
Yeah,
Okay.
so an error per second metric is effectively what you're looking for.
Right.
And that would be the same magnitude.
That's bigger bar worse though.
Yes,
So
exactly.
wait,
well,
so
do it inverted.
Now we, now we need to abstract away
Yeah, do
again.
it inverted. Do it inverted. Yeah,
Correct,
but I'm really
yeah.
excited about that. I'm excited about this one here, Click-to-Photon latency.
Yeah.
So I think I might have mentioned that before, Jefferson's.
That we should talk about, yeah.
Okay. Well, this is a completely software version of Click-to-Photon, so no hardware needed. It looks at a USB event to say, hey, there was a USB event that happened. And oh, by the way, I'm doing a frame right now.
Yeah.
So that USB event is probably associated with this frame. Let's pretend it is, and then measure the pipeline all the way until I know this frame gets flipped, and that's Click-to-Photon. So that's going to be like 80%, 85% of the way to getting you a hardware-free, photon measurement.
Yeah, so for Click-to-Photon is exactly what it sounds like if you think through it, where it's you click or you have some input, how long until there's an actual like light representation of that event. And the way that we and pretty much everyone else, so before other hardware tools is basically high-speed camera,
Yep.
that's what you did.
Yep.
And now there's things like LDAT, RLA, but some kind of physical hardware tool is required to measure. So this is software, which is interesting.
Yeah, and I think that's a very cool thing. But it's not enough. You need a hardware one.
Yeah.
That's right, yeah, baby.
Yeah.
Yeah. So shout out to Ruslan, who was the original LDAT creator. We have at Intel created our own version of LDAT. It's called LMT. I'm the firmware developer for this one.
You are?
I am.
Okay.
Yeah, and I also did the app. Yeah.
Cool.
So, but the team in Toronto did a great job on the board. It does basically very similar to LDAT. Ours is open. You'll see it out on GitHub. Schematics will be up there, and effectively this will be rolled out in the next couple of hopefully weeks.
Like PCB schematics?
I'll put the whole thing up there. Yeah. Yeah.
I'm just thinking, like, in terms of video content, we have long talked about taking a PCB schematic to Taiwan and having it made.
Oh, that'd be great. You know what?
Yeah.
I just did my own PCB as part of this project, and it's super easy to do online.
Okay.
You can actually just submit the thing, and the board comes back a couple weeks later. Yeah, it's crazy. Yeah. Yeah.
So, okay, so this is your hardware solution to this.
Yeah.
What are the components of this? Like,
Well, this is an ATX Mega 32U, I think. It basically is the microcontroller. On the back side over here, there's a photodiode.
Okay.
And effectively, here is a click. There's got a little mouse thing. And over here, you can instrument a hardware mouse. These are kind of serial ports for external RGB sensors.
When you say a mouse thing for this one, you mean there's like basically a button on a wire?
Yeah, we basically have a little mouse simulator.
Yeah.
And you can click the mouse. The mouse event goes into the microcontroller, which converts it to a USB event. It comes out the USB port and goes over to the PC.
So does that have a known latency, I guess?
We measure it, exactly.
Okay.
So we're gonna record the time the click happened in the microcontroller. And that event's gonna go over. And when it shows up in the PC, it goes into a host app, which we're also making available on public source.
Okay.
And the host app will say, hey, there's a button click, and it'll if you have a game running, it'll light something. And then the photo detector over here sees the light change and records it back on the microcontroller.
Right.
And then the microcontroller is communicating over each HID back to the host app to kind of do analysis.
Cool. Yeah, we'll have at GN we'll have a whole separate video on it, I'm sure. But I don't want to get into the rabbit hole of it too much. But there's a lot of like really sensitive aspects of test setup for these physical hardware tools where you have to understand. So, for example, a really quick and simple example, but using game interfaces and menus, it seems like a really tempting way to measure the response.
Yeah, that's bad.
But it's not right.
Yeah, yeah.
And same thing too, like some games have a fixed amount of frames for which the attack will animate. As an example, you need to factor that in.
Yeah.
So there's a lot of landmines that, if distributed just at large, the community, I think we need to put some material out.
There's going to have to be. I mean, for us, we're still in like baking mode for this thing. So as you know, it's going to be a little bit.
Yeah,
I'm pretty excited about it. So back over here, Click-to-Photon. I think you're going to be all over. Eventually, our LMT will integrate with PresentMon, so you'll see the LMT events show up in PresentMon.
So LMT to me strikes me as something that definitely should be in review toolboxes. But this one for end users, since it'll be in software, is more approachable.
Yeah, totally.
So think that FrameView does some kind of PC latency metric. Well, actually, I know it does a PC latency. I'm not very familiar with FrameView. We don't use it here, but so there's a couple tools. There's FrameView that does something I'm not familiar with. There's Click-to-Photon through PresentMon 2 now, I guess, which is in beta.
Right now, it's just with a few key press.
Okay.
But we'll be making a public release in the next month or so.
Okay.
So stay tuned through a little more QA, get some feedback from you. As long as it's all good, it'll be going up on the web.
And so anyone who wants to follow that so you can download it and use it when it's ready, we will probably do the update in hardware news. We normally use it through CLI. There is an interface.
There is.
I know you want to show the interface.
I do want to show it.
Okay.
I do want to show
all
it.
Right.
So why don't we cut to that and pull up the demo.
Okay. Okay, so we popped up PresentMon, installed it on a test machine. I'm just running superposition here. It was the quickest thing I had to launch. And then this overlay you've blown up for presentation purposes. It can be resized.
It can resize any way you want. Wider, smaller, bigger, fonts are changeable, the whole thing.
The quick recap is Tom kind of went through the PresentMon interface, which is over there. We've got B-roll we'll show of it. You configured a set of charts in the overlay. And now, Tom, can you walk me through kind of...
what is this telling us now?
Yeah, and I mean... I know.
You know.
But I do, this is something we didn't spend a ton of time on last time because we're so focused on GPU busy.
Yeah.
And this is something that an end user can actually do.
Yep.
So I think it's useful.
Well, the way to think about it is I've got two clusters I set up here. One is sort of a CPU image. The other one is sort of GPU-y. On the CPU side, I've got frame time, CPU busy, and CPU wait. Now, if you look at it, you can see the red is busy and the green is wait. Normally, you want some wait on the CPU if you're trying to, say, not bottleneck your GPU. So in this case, I've got about 3 milliseconds or 4 milliseconds busy and about 2 milliseconds waiting, which is actually probably pretty good. It means that the CPU did all of its work, had a little bit of head time, hung out a little bit. Now, if you look down on the GPU, you can see I've got frame time set up, GPU busy, GPU wait, and here you see, wow, my GPU is busy 5.5 milliseconds out of 5.7, so it's basically pegged, right? And so very quickly you know, okay, if I want my frames higher than 170, I need to lower my GPU settings. My CPU's just fine, right?
I think that's a good way to relate it back. Where if I don't know, I'm sure a lot of people do this in the competitive scene, but if you're someone who's targeting a certain frame rate or just a really high frame rate, and you're struggling to figure out which settings to drop,
this is the way to do it.
That would be an easier way.
Right, another cool thing is now that you've got these things set up, you can also see some telemetry. So this is coming directly from the GPU and your CPU and your system. You can see the power is running about 163 watts, which is pretty high. Your GPU is pretty cool at 60C, and you can see the utilization is kind of 100%, then a little bit lower than 100%, so it's doing pretty good. This is actually 98, so it's like, bubbling up near the top.
And the scale can be adjusted in the software too.
Yeah, you can turn off the auto scale.
Yeah.
So I think it's a pretty easy thing to do. Of course, it captures as well, so there's a little hotkey to do captures, and you can adjust, exactly how much updating you want to do. There's histograms. It's pretty full feature.
I want to ask overhead. So there's other reasons too, but one of the main reasons we use command prompt for all of our capture tools is minimize overhead.
Right.
So do you happen to know off the top of your head what the impact is?
When you run a capture on this, we turn off the overlay.
Oh, okay.
So there's no impact that we've been able to measure for capturing with the tool installed of the overlay versus the script, because it's basically the same thing.
And I would assume there's at least a little bit of overhead with just PresentMon in general.
There is a tiny bit.
But there's, I mean, there's not really.
Yeah, it's not perceptible. We've correlated Fraps, PresentMon, FrameView, and a lot of derivative tools, and they all get the same.
About the same, Okay.
My guys know I love histograms. Okay, so nowhere else. This is the only place.
Let's do
I'm going to do a
histogram.
histogram. So let's got some variation to it. How about we do power, right? So GPU power is fluctuating. So instead of a graph, you say, I want to do, I don't want to do average. Why can't I do a histogram?
The development team's going to
you know
hear
what
about
it is?
this.
It's because I got two of them all back.
Oh, okay.
So let's get rid of temperature real quick. Oh, please work. I don't want to ruin Ray's day. So graph. Oh, you know what it is? I say graph, and then instead of line, you say histogram.
Okay.
Ooh, that was close.
I was worried we just cost someone's job.
Yes. So check it out.
Histogram guys, no more.
No, histogram guy's gone. So how many bins you can configure your histogram, your autoscaler. So let's do a few less bins. And now you can see kind of a distribution over time of power, right? That's actually the right view for these high variance things, and you want to look at it over time. And you can do percentiles and various. We're adding I hope we're adding a capability to plot multiple different variables on the same histogram
Yeah.
can be pretty cool.
It's interesting too to see this pattern.
Yeah.
Where it's the game or the engine or whatever's doing something, I guess.
Well, again, but you're at 96 to 100, so I suspect that's
the scale. Okay.
Yeah, it's auto scaling, so it's very little, but still, you know, substantial. I think, you know, to me, the tool helps give that next click down into what's going on between CPU and GPU balance. So I think there's work to be done here. You know, if people are using this, they have ideas, you know, put them in your chat, we'll read it.
Right.
You know, there's lots of stuff to be done. A stack graph, I think, is going to be very useful here. And yeah, we're going to keep working on it.
Cool. So there is going to be a beta soon, if not already.
It should be out soon.
Okay.
Gaming.intel.com or something.
Yeah.
But there's also a GitHub repository that has all the builds.
Right.
So if you just Google PresentMon, you'll get there.
Yeah. Cool. So check it out if you haven't. Like I said, this PresentMon we've been using for, I don't know, probably like, I don't know when it came out.
It's about 10 years.
Yeah.
It's about 10 years.
It's about 10 years now. As command line, the interface iteration kind of came out in the last, I don't know, year or two. And so check it out if you want to get some of the numbers that we get. But as always, Tom, thank you for joining.
Great to see you again.
Yeah.
Thanks for having me.
And check out the other videos. We'll see you all next time.